Wonderful. Hi, all. My name is Jenny Wilson, and I am faculty in the math department here at the university. I study an area called topology, and I wanted to talk today a little bit about how I think about that. Topology is the study of shapes. So today we're going to be looking at surfaces and how we can understand surfaces by studying loops on those surfaces. So I wanted to start, with the demo camera, I wanted to start with a little demonstration. This is a cylinder that I made by taking a piece of construction paper, I folded it around, and I taped it back to itself. And watch what happens if I take my scissors and I cut out this cylinder right along the loop through its center. Then when I'm done, as you maybe expect, what I get is two pieces, two smaller copies of the cylinder. Okay, so this is what happens when we cut out a cylinder. The first question for this talk is what is going to happen if we do the same thing with the Mobius band? So I'm hoping I can get some volunteers to come up. In fact, we have enough Mobius bands, I think, for everybody. If anybody wants to come up and help me perform this experiment, come grab, anybody who's able to use scissors, please come up, grab a Mobius band and grab some scissors and see what happens when you cut out along the center. In fact, I will come and help bring these out. Would you like to give this a try?
Thank you.
Yeah, thank you. Thanks. Thank you. Here, let me hand out more. A Mobius band, that's an excellent question. This is a Mobius band, and we'll get into more details on the question of what a Mobius band is in just a second. Would anybody else like to? You're good? Anybody else for a Mobius band? Please. All right, and let me do one for the demo camera here too. So I'm going to take my Mobius band, make a snip to make it easier for myself, and just cut straight along the midline of this Mobius band. And what are folks getting? Yeah, that's right. So when we're done cutting it out, instead of getting two pieces, we just got one piece. And somehow it's even more twisted than the piece we started with. So that's interesting. All right. So somebody just asked the question of what is a Mobius band? And let me answer that question. So the way I made these Mobius bands is I took my sheet of paper, I took my strip of paper. If I wanted to make a cylinder, I would just fold it like this and tape it up. But to make a Mobius band, before I taped it together, I introduced a twist. I just took one of the edges and I flipped it over, and then I taped it shut. So my next question for us all is what happens if we try another variation on this problem? This time, instead of twisting it just once and taping it shut to make a Mobius band, I'm going to twist it. Oh, I'm sorry, I'm not on the camera. I apologize. I'm going to twist it a second time. So now this is a shape with two twists in it. And the question is, what will happen now if I do the same thing? I'm going to tape it shut, and I'm going to cut it out along the midline. So maybe we can take an audience poll of what we expect will happen, and let me remind us what we've seen so far. We've seen if I have a cylinder with 0 twists, I get 2 pieces. A Mobius band had 1 twist in it. When I cut it out, I just got 1 piece. So what do we think is going to happen? I just put 2 twists into this piece of paper. Who thinks we're going to get 1 piece? Show of hands. Who thinks we're going to get 2 pieces? Show of hands. And who thinks we're going to get some other number of pieces? Show of hands.
I like that number.
All right, so let's try it. Let's give it a shot. I'm going to take my 2-twist sheet of paper, and I'm going to cut it right along the center line. Oh, and I didn't advance the slides here. Side story. It turns out there's a math department in Morelia in Mexico that has a Mobius band jungle gym, which I got to climb on. It's the highlight of my life so far. This is the Mobius band in Morelia. Okay. Great. So here's the question we're answering right now. How many pieces do we get if we twist the Mobius band twice before we cut along the midline? I'm almost done. And let's see. Look. So this time we got 2 pieces, except they're linked together. Ooh. Yeah. So I propose the question for everybody here, how does this generalize? What do we think is going to happen if I did 3 twists before I taped it? Or 10 twists? Or 837 twists? What's the principle at play here that tells me how many pieces I'm going to get if I twist my strip that many times before I tape it together and cut along the midline? Is anybody willing to venture a guess? Yeah. Yeah, so how many pieces of paper do you think? How many separate pieces do you think I will get if I twist it 3 times and then cut it out? Any guesses? So we've got a guess for 2. 1. So I think in this case the answer is 1. What do you think it is about the number 3? It's an odd number. That's right. Yeah, so it turns out it has to do, that was a good guess. I like all this. Math is all about making guesses and then being wrong a lot of the time and then learning something. This is how we go. Yeah, it turns out it has to do with whether it's an even or an odd number of twists. And to see why that is, I've brought here's my strip of paper that I have. Oh, I should try to stay under the camera. My strip of paper where I've colored the 2 sides a different color. And let me demonstrate what happens. If I just fold this into a cylinder, note the midline separates it into the blue section of paper and the orange section of paper. So right now, if I cut along the midline, I'm going to separate this piece of paper into blue and orange. But watch, when I make my Mobius band, I introduce a twist. And now the blue side is connected to the orange side and vice versa. So now I'm not going to separate this piece of paper when I cut along the midline. I'm going to still just have 1 piece when I'm done. But if I twist it again, then once again, the orange meets up with the orange side and the blue meets up with the blue side. And again, the midline separates the blue part from the orange part. And you can see this will still happen as I keep twisting. If I use an odd number of twists, I'm going to end up with 1 continuous piece after I cut it out. And if I do an even number of twists, the midline will separate the blue and the orange. Okay, great. So I think we understand Mobius bands and their variations. And here's the solution. So the answer is an even number of twists. I'm going to get 2 pieces after I cut. Odd number of twists, I get 1 piece. Here's a picture of this guy. And the reasoning is that it depends whether the midline separates the blue or the orange or not. Okay. And so the next question is, well, how can we use the same principle when we're studying other surfaces? And today I've brought a few examples of other surfaces with me. This is what I'd call a sphere, a 2-dimensional sphere. This is what I'd call a torus. This is what I would call a genus 2 surface. And again, I would like to consider this question about what happens when I draw loops on these surfaces and then cut out the loops. And one of the most basic questions I can ask about that operation is how many different pieces am I going to get? If I take these surfaces, I draw a loop on the surface and I cut it out, how many pieces? The mathematical jargon for that is the number of connected components. Okay. All right, so it is a mathematical theorem called the Jordan curve theorem that the answer to this question for a sphere is as follows. If I draw any loop on the surface of this ball, on the sphere, that loop is always going to separate the sphere into two pieces. It's always going to be the case that I can, say, color the inside of my loop in, I don't know, pink in this case, and I will have a distinct pink piece and blue piece. It's true no matter what loop I draw, as long as the loop doesn't intersect itself, as long as the loop doesn't cross over itself. Okay. In contrast, here are my tori. I have another challenge for the audience, and folks are welcome to come up and grab a torus if you want. Maybe I'll hand some tori around. Some tori. Want a tori? I should get some more tori. I borrowed these tori from my infant. They're one of his toys. Okay, and so the challenge is, can you find some loops on these tori that have the feature that if you cut out around that loop, you would end up with only one piece? Any volunteers? So again, the question is, so we saw for the sphere, no matter what loop you draw, if you cut out that loop, you're going to get two pieces. And now the question is for the torus is math jargon for the surface of a donut. If we look at the torus, can you find me a loop where if you cut out along that loop, I would just get one piece? It would not disconnect the torus. Any ideas? I see one over there. Show me that loop that you were just pointing to. Perfect. Yeah, that's right. That's a loop I would call, I think that's a meridian. No, that's the longitudinal loop. I get those words confused. Anyways, you're absolutely right. So, so here is the question. Does the Jordan curve theorem hold for the torus? And the answer is no. So here are two examples of loops on the torus where if you cut them out, if you took your scissors and you cut along these loops, you would end up with just one piece. And so this is one of the ways that a topologist can distinguish between a sphere, the surface of a sphere, and the surface of a donut, is that on the surface of a donut, we have these loops with this weird property that if you cut out along that loop, you still just get one piece. Okay. Oh, right. So here's a consequence of that I wanted to mention. A consequence of this result on a sphere, and let's see if I can get the document camera working for this, is if I have any loop on the surface of a sphere, then the theorem says I can color the inside red, and I'm going to have, or pink here, I'm going to have a distinct pink region and blue region on the surface of my sphere. What this means, if I have any second loop, so here is a second loop that I'm drawing in yellow, also on the surface of my sphere. I claim that the yellow loop and the pink loop have to intersect each other an even number of times. They might intersect 0 times, but they have to cross each other an even number of times. And the reason is, well, in this picture, my yellow loop starts in the blue region, as I walk along this loop, here I cross over my pink loop. Now the yellow enters the pink region. Well, the yellow loop needs to get back to its starting point, so it has to cross the pink loop a second time to get back into the blue region in order to get back to its starting point. So that means if it crosses once to get into the red, it has to cross again to get back into the blue. And extrapolating from this reasoning, we see that they have to cross an even number of times. And so this is another feature of a sphere. It means any two loops have to cross each other an even number of times. And that's wrong. Again, a way that a topologist can distinguish a sphere from a torus is that here on this torus, we have a pair of loops that cross each other exactly one time. This is what topologists call the intersection number of these two loops. So you need to be on a space other than a sphere, like a torus, in order for there to exist loops that have intersection number 1, like this.
I have a question.
Yeah, please.
So when he was drawing a loop around his torus, he was
Yeah.
doing sort of like a spiral
Oh, yeah.
and was thinking about whether that would. But what if you put one in the very center?
What if you put one in the very center? Excellent. Yeah, so these are great questions. So the questions are, as I understand, like there are many other loops you can draw in a torus. And which of those loops are going to disconnect it or not? And it's true in general. If I draw, here's this is a genus 2 surface and not a torus, but I handed out all my tori, so I'll use this one. I mean, it's certainly true that you can find loops that will cut the torus into two pieces. So for example, if I just draw a little loop around like this little region right here, then if I cut out that loop, I'm going to get two pieces. That's true for sure. And so the question is subtle. It's not obvious what's going to happen for a given loop. If you took your torus and you took this loop that's right around the center like this, it turns out that loop is, from a topologist perspective, that loop is the same as this blue loop here. And it turns out that that will not disconnect the surface. You will end up with one piece if you cut along that loop around the center. So that's a great example. And let me think. I think it is also true if you drew a loop that sort of spiraled around the outside, then absolutely you can spiral, as many times as you want around the outside of this torus. And that is a great question I would have to think about. I mean, or we'd have to actually do the experiment to see whether that disconnects the surface or not. My suspicion is that it would not, but I don't know. I'd have to think about that. That is an excellent question. I love these questions. All right. And I wanted to, I guess we're going to wrap up in a minute. I wanted to point out a generalization of this question. So on a genus 2 surface, this is my genus 2 surface, we can do something, we can extend this even further. On the genus 2 surface, I claim it's possible to actually find two non-overlapping loops, non-crossing loops, with the property that you can cut out both of them and still not disconnect the surface. And one way that we can do that, to the question is, can you find two loops? If you cut out both, you'll still have just one piece. Here are an example of two of these loops. I can cut out this loop here, and I can cut out that loop here, and I will still just have one piece. So this is something that distinguishes the genus 2 surface from the torus. This is something that you cannot do on a torus. Okay. And great. That's it. So a summary of what we talked about today is, from a topologist point of view, one thing that we can do to distinguish different surfaces is we can ask the question, on the surface, can I find a loop that does not separate the surface into two pieces? Can I find a loop with the property that if I cut it out, I just get one piece? And we saw that if our surface is something like the sphere or a cylinder or a piece of the plane, the answer is no. But for surfaces like the torus or the genus 2 surface or the Mobius band? The answer is yes. All right. And at the very end, we saw a teaser that, in fact, we can distinguish even more surfaces by looking for collections of loops, where if I cut out all of them all at once, I don't separate the surface. And this is one way that a topologist can tell whether two different surfaces are topologically distinct from one another. All right. Thank you. Thank you, everybody, for coming, and thank you for participating. I'm happy to answer questions or invite anyone to play with these toys if they'd like.
So how do you divide topology? Are you like an engineer or something? Or?
I am in pure mathematics. Oh, so the question was, am I an engineer, or how did I get into topology? And I am in the most theoretical of the theoretical of mathematics. So unfortunately, like the math I do has no direct bearing on engineering or other applied fields, but it is very abstract and, in my opinion, very beautiful.
It's just like thought.
We just think, that's right. The objects are very abstractly defined. And yeah, thank you so much for coming. Thanks for participating.